lecture 33 of our series on numerical methods in civil engineering, we will continue with our discussion on orthogonal polynomials. Recall that in the last lecture I talked about Chebyshev polynomials, and we ended the lecture while talking about a very important property of Chebyshev polynomials, namely the property that in the interval -1 to 1 the Chebyshev polynomial 2 to the power 1 minus n Tn has the smallest maximum norm among all polynomials with coefficient equal to 1, right. Among all polynomials with coefficient equal to 1, the Chebyshev polynomial has the lowest maximum norm. That means that at any point in the interval, if I plot any other polynomial with coefficient 1 and I plot the Chebyshev polynomial 2 to the power 1 minus n times Tn, the magnitude of the Chebyshev polynomial will be smaller than any other polynomial, right. Now, by dividing each term of any polynomial of order n, we can ensure that the leading term of that polynomial is 1. So, for the entire set of polynomials of order n suitably scaled, we can say that the Chebyshev polynomial has the lowest maximum norm. And we saw that this has particular implications if we want to find out the optimum location of the grid points. What is the optimum location of the grid points? Well, I know a certain interval, say a b, and I want to find out where in that interval should I place my grid points, where should I know the function values in order to minimize the error, right. So, that the error any polynomial approximation will have a truncation error, right. And if I want to minimize the truncation error, it turns out that it depends a lot on where I sample my function, right, and that is where the Chebyshev polynomial comes in. Suppose we wish to locate the grid points optimally in the interval of interest where we are trying to do a polynomial interpolation, and that interval may be a b, but by doing a suitable change of variables, transformation of variables like this, we can transform that into -1 1 and x becomes t, right. And I know that in this interval the remainder term in the interpolation is like this. This we have seen earlier, right, t minus t0, t minus t1, t up to t minus tm, f m plus 1 xi divided by factorial m plus 1, where t0, t1 through tm are the grid points. Now, suppose there is a dependence on this in this error term on t, right, on t, right, because first of all xi must belong to an interval which is the smallest interval that includes all these points, right. So, xi depends on t, right. But if we assume that f to the power m plus 1 xi is bounded, right, that it is bounded, right, then the remainder term can be written like this, where I can think of b as the bound, right. So, instead of writing it like this, I can represent this whole thing as b, and then I get this expression, right, b into t minus t0, t minus t1, t minus t2, t minus tm, right. So, the zeros of this are at t0, t1, t2 through tm. Now, since the remainder is a polynomial of order m plus 1, the zeros of the remainder are about the same as the 0 of the first neglected term. They are not exactly the same, because I have ignored the dependency on t of f m plus 1 xi. This should be t, right, I am sorry, it is the same thing because there is a transformation of variables, right. So, I have ignored the dependency of f m plus 1 z on t, right, but it turns out that since I have ignored that, I can assume that the zeros of this remainder are the same as the first neglected term in the series, right. Now, if we plot that error graphically, this error basically, if I plot it graphically, then I will see that it will be something like this, right. Why? Because it has to be 0 at t0, right. It will be 0 at t1, it will be 0 at t2, t2, t3 and so on and so forth, right. So, basically it will be 0 at all these points at t equal to t0, t equal to t1, t2 and t3. However, look at this, if instead of doing a polynomial approximation, if I try to expand the function in a Taylor series about t0, right. If I try to expand the function, so why do we do an interpolation? Well, we know the function values at certain points and we want to know the function value at some other point where the function value is not known, right. That is why I do interpolation. Now, suppose instead of doing that, I say that I know the function value at a certain point, right, and maybe I know higher order derivatives of that function also at that point. I can expand that function in a Taylor series about that point, right. I can expand it in a Taylor series, and if I expand, I can find out the value at another point, right. But the error in a Taylor series is of this form, x minus x0 to the power m plus 1, right, given that this is the remainder term, right, that is of this order. So, if I expand, if I expand the function in a Taylor series about t0, right, the error term, which is like this, will be like this. As you go away from t0, the point where I know the function value and its derivatives, the error is going to go as a power in, again this should be t minus t0, I apologize. So, t minus t0 to the power m plus 1, right. So, it is going to increase like this. However, if we do, if our error term is of this form, right, you can see that it will be oscillatory, right, it will be oscillatory. But more than that, we want something more than that. We not only want it to be oscillatory, we do not want it to increase monotonically, but we also want these values to be bounded, right. I want that error term to be as small as possible, right. I do not want it to grow monotonically. That is good. It is oscillatory. That's one good thing. But another requirement is that those values, right, they mustn't be very big, right, and that is where my Chebyshev. So any interpolation, any polynomial interpolation is going to be better than Taylor series. You can see that, right. This is oscillatory and this is growing monotonically. But if I locate my grid points at the location of the zeros of the Chebyshev polynomial, in that case I am assured that this thing will also be the lowest possible, this error term will also have the lowest possible magnitude, right. So, then it will not only be oscillatory, but it will also have the smallest possible magnitude. So, hence it is obvious that while the error due to polynomial interpolation is oscillatory and bounded, the error due to a Taylor series approximation increases continuously with distance from t0. The question obviously arises as to the optimum location of the grid points t0, t1 through tm, so as to minimize that error y is equal to bt minus t0 and so on and so forth, right. We recall that between -1 and 1, the polynomial 2 to the power minus m t m plus 1 has the lowest maximum norm for a function of this form, right. Why of this form? Because this is the form where the leading order term is going to have coefficient 1, right. So, it has the lowest maximum norm, right. Thus, if we choose the grid points t0, t1, tm to be the zeros of the Chebyshev polynomial of order m plus 1, right, of order, this is after all the Chebyshev polynomial of, right. So, this is a m plus 1th order polynomial. So, we choose t0, t1, tm to be the zeros of the Chebyshev polynomial of order m plus 1, that is tk is to be these, right, which we saw earlier, right. Then the error function would become this function, would become this function 2 to the power minus m tm plus 1, right. The error function would basically become this function. The coefficient b would appear for any choice of grid point, so it does not matter, right. B is going to be there, right, wherever I choose t0, so that is not important, right. I am just concerned with this part, right. I am ignoring the b because b is constant. Whatever t0, t1 I take, b is always going to be there, right. So, I am looking at this part and I am trying to minimize the norm of the magnitude of this part, right, the magnitude of the function due to this part. Thus, we would be guaranteed the error would have the minimum possible value in the interval -1, 1, and thus by extension a b if the grid points are chosen to be the zeros of T m plus 1, right. And interpolations that use these grid points are known as Chebyshev interpolations, right. Is that clear? They might choose a different polynomial basis, right, but the grid points, if they choose like that, right, then we are assured that the error term would behave like the T m plus 1, right, to the power 2 into m 2 to the power m minus 1 times T m plus 1, right. Is that clear, right? So, Chebyshev interpolation is much better than equidistant interpolation. We have seen that before, but just to recapitulate, because of the restriction it places on the error, Chebyshev interpolations are also particularly effective near the ends of the interval, whereas we have seen earlier equidistant interpolation gives large errors. I looked at this example earlier, right, where we are trying to fit this function, right, we have no function values for this one, and I am trying to fit a polynomial to this, and if I do equidistant interpolation I get something like this, very large errors near the endpoints, and this I do for these errors are particularly severe. These errors are particularly severe for higher order polynomials. As you increase the order, these errors become large, and I think at that time we saw, or maybe we did not, in case if you use a Chebyshev instead of using equidistant interpolation, if you use Chebyshev interpolation, right, basically you choose your grid points to be the zeros of the Chebyshev polynomial of order T m, then in that case the error is going to be much smaller. So, does this mean that we should use Chebyshev interpolation instead of equidistant interpolation all the time? Well, maybe not, right, because finding the grid points of Chebyshev interpolation involves evaluating trigonometric functions, right. An evaluation of trigonometric functions is, you can see it, we need to evaluate these cos terms, right, these terms, right. In order to find the zeros we need to evaluate these terms. Evaluation of trigonometric functions is computationally expensive. Doing so repeatedly for large problems may impose a heavy computational burden. Thus, using Chebyshev interpolation is probably best for higher order interpolations, right, particularly because higher order interpolations have this problem. Higher order interpolations have this problem, right. So, for these higher order interpolants, it is better to use Chebyshev interpolation, to use your grid points at the zeros of the Chebyshev function, which is of the order of the remainder, right. But in case you do using lower order interpolants, then maybe you can get away with using equidistant interpolation, right. Maybe it is not that bad if you use equidistant interpolation, because, well, you are going to get larger errors, that is true, your truncation error is going to be larger, but always in numerical analysis it is all a question of weighing the costs and the benefits, right. So, how much computational expense, additional computational expense, what is the gain in accuracy, those things become important, right. And people have done people who have run a lot of simulations, they have reached the conclusion that, well, you should probably use Chebyshev interpolation for higher order polynomials, right, because then the error just becomes too big, right, and it is worth paying the price of calculating those the grid points, right, calculating the grid points using for the Chebyshev polynomial. But for lower order interpolants, maybe you can get away with using equidistant interpolation. So, then using Chebyshev interpolation is probably best for higher order interpolations, that is n greater than 2 to the power root m, right. So, I have m plus 1 grid points, right, but I have, so m plus 1 grid points, the highest order polynomial I can fit to that is m, right, I can fit an mth order polynomial, but instead of fitting an mth order polynomial, I am going to fit a polynomial of a much lower order, and what is that much lower order? N, right, n, and if n is less than 2 to the power root m, then I am fine doing equidistant interpolation, but if n is greater than 2 to the power root m, then I should go for Chebyshev interpolation, right, Chebyshev interpolation. For n greater than 2 to the power root m, well, this is exactly why we have that behavior. It is because for n greater than 2 to the power root m, equidistant interpolation using polynomials have high degree, are ill conditioned, right, are ill conditioned. What does ill conditioning mean? Well, it means that if you have a slight change in the function value, your interpolant is going to change a lot, right, it is going to change a lot. An interpolant is ill conditioned when the values which one gets by equidistant interpolation with a polynomial of high degree is very sensitive to disturbances in the values of the function, and this is particularly true near the ends of the interval. Chebyshev well, so that's enough about Chebyshev polynomials in particular. Now I want to take a step back and talk about orthogonal polynomials in general. Chebyshev polynomials are just a particular instance of orthogonal polynomials, right. So they are orthogonal to each other with respect to the weighting function 1 minus x squared to the power minus half. Why do we want to talk about orthogonal polynomials? Well, because orthogonal polynomials form a basis for the infinite dimensional function space. If I have an infinite number of base orthogonal polynomials, a series of orthogonal polynomials infinite in number, they will form a basis for the infinite dimensional function space, right. In addition, they are easy to manipulate, have good convergence properties, and give a well conditioned representation of the function, right. Well conditioned means that minor changes in function values will not lead to major changes in the values of the interpolants. Because of this, expansion of functions in terms of orthogonal polynomials is very useful, and we want to talk about it in general, right. To motivate this discussion, let us recall what we want to do. We are trying to find an approximation to a function in terms of a family of polynomials of increased order, right, which are orthogonal to each other in some sense, right, they are orthogonal to each other. If we think of these functions as vectors, right, just this is a mental exercise, right. If I think of those functions as vectors, and if I know if the known function values at the grid points, if I think of that as a vector, the more the grid points, larger the dimension of the vector. That is clear, right. So I have grid points located, right, and I evaluate the function values at those grid points, right. So the more the number of grid points, the larger the dimension of that vector, right. So if I have a function, I evaluate it at each of those grid points, I can write it as a vector, right, and the more the grid points, the longer that vector, right. So the dimension of the space, the dimension of the vector, larger the dimension of the vector space spanned by the vector, right. So larger the dimension of the vector space spanned. So if I have 15 points, 15 grid points, what is the dimension of the vector space? It is going to be 15, right. If it is going to be 15. So that means that there must be 15 basis functions for that space, right. There must be 15 independent vectors for that space. Any vector of size 15 can be written as a linear combination of those 15 independent base vectors. Thus, a function whose values are known at n grid points can be thought of as an n dimensional vector that spans a n dimensional vector space. And then we go back to function. Thus, an n dimensional function space has n basis functions, right. So here, instead of thinking of, so vector is just for making things clear, because it's something that probably most of you are familiar with, right. But actually we are talking about functions, right, and we are talking about the basis how many basis functions we need, and it turns out that the number of basis functions we need depends on the number of grid points. Our approximation, that is representation of the original function, thus becomes richer as the number of grid points and the number of known function values increases, simply because the dimensions of the space of functions that can be used to construct the approximation increases, right. So, now as the dimension increases, right, the number of basis functions also increase, right. So, it becomes in a sense richer, right, my basis becomes more, it can represent more complexity, right. The basis functions phi 0, phi 1, phi 2 are linearly independent if they satisfy this condition, only if all of the coefficients are 0. So, these functions phi j are linearly independent if I multiply all those phi j's with some arbitrary constants, and if in case they turn out to be 0, that means each of those constants have to be 0. What does it basically means? It means that I cannot express any one of those phi j's as a linear combination of the remaining phi j's. These functions are known as basis functions because any function belonging to the n dimensional space can be written as a linear combination of these basis functions. So, if phi n is any arbitrary member of that n dimensional function space, right, I can write phi n as a linear combination of my basis functions for that space. If the basis functions, in addition to being linearly independent, are also orthogonal to each other, we have an orthogonal system of functions like the Chebyshev polynomials, right. They represent an orthogonal series of functions, right, orthogonal system of functions. So, given the dimension of the function space determined by the size of the vector of function values, right. So, my vector of function values has a certain size, evaluate the function at all the grid points, I get a vector, that vector has a certain size, that gives me the dimension of the function space, right. How do we construct, and knowing a set of basis functions, how do we construct the best approximation to the function f, right. So, I know I have a certain function f, I know the size of my function space because that function is given only at certain points, right, at a finite number of points, right. So, I have a finite dimensional function space, right, and given, and I know the basis functions for that function space. So, how am I going to get the best approximation to f from by taking a linear combination of those basis functions, right. The solution to the approximation problem in the Euclidean norm is that linear combination of basis functions whose distance from the target function f is minimum. So, you can imagine, right. So, I have these basis functions, I construct a linear combination, I construct a function by taking a linear combination of those basis functions, and that function that I construct is going to be the best possible approximation, right, if its distance from the known function f is minimum. And what do I mean distance? Well, I mean distance in the sense of a Euclidean distance, right, and we are going to talk about that in more detail, right. So, if we denote this distance as the error vector f star minus f, the magnitude or norm of this vector is going to be a minimum when f star minus f is perpendicular to the space spanned by phi 0, phi 1, phi n minus 1. Think of very simple geometry, right. I have a straight line, right. I want to find a point not lying on the straight line whose distance is minimum, right. So, and it has on a certain path, right. So, that will be it has to be perpendicular, right, it has to be perpendicular to the straight line, right. It has to be if I draw a line from that point to the straight line, if that line is perpendicular, then the distance is minimum, right. So, similar exactly we have something like this. So, f star minus f, right, f star is what I construct, right, what I construct by taking a linear combination of my basis functions. If the difference between f star and f star minus f is orthogonal, is perpendicular to the space spanned by these functions, then I know that the magnitude of this error vector is going to be a minimum, right. Thus, the coefficients C0, C1 through Cn minus 1 are determined to satisfy the requirement that this Euclidean norm sigma Cj phi j, which is what I construct like f star, right, sigma Cj phi j minus f, if I take the norm of that square, that has got to be the minimum, that has got to be the small, have to have the smallest possible value, and whatever value, whatever coefficient Cj, make this norm the smallest possible value, make this norm assume the smallest possible value, those are the coefficients of my best approximation. Those coefficients multiplied by my basis functions are going to give me the best approximation. Now, the squared norm, this norm is also expressed in terms of an inner product, and we define an inner product like this. This is the notation, first bracket, two functions f g, that means I am taking the inner product of f and g, and the inner product is always with respect to a certain weighting function, right, and that weighting function is w of x. So, what that is in the continuous case. In the continuous case, you can write the inner product in terms of an integral, right. What about the discrete case, where I just know the function values at a certain number of grid points? Well, in that case, we construct the inner product like this: sigma I is equal to 0, f of x I, g of x I, w x I. So, I know the function values at points x I evaluate the function f at x I, evaluate the function g at x I, multiply it by the value of the weight function at x I, sum them together, that gives me my inner product for the discrete case. And the inner product of two functions obeys the same rules as your vector inner product, vector dot product, right. What are those rules? Well, f g is equal to g f, that is commutativity, right. It's linearity, C1f plus C2g operating on phi, inner product with phi, sorry, not operating on phi, inner product with phi, that is going to give me C1 f phi, inner product of f and phi, plus C2 g, inner product g of phi, right, that is linearity. Inner product of f and f is always greater than 0 for any f not equal to 0. When I say a function is not equal to 0, I mean the function is never 0 at any point in its domain, right, and its domain being the interval on which it is defined, right. So, for all x belonging to a b, f is not equal to 0, only then do I say that f is not 0, right. So, f dot f comma f is greater than 0 for all f not equal to 0 for all x, right, and f comma f is equal to 0 only if f is equal to 0 at every point x, right. This is very important, we are going to use that quite often. So, f comma f is equal to 0 only if f is equal to 0 at all points x in the interval. From linearity, therefore, if I take this inner product, the inner product of Cj phi j, j is equal to 0 to n minus 1 with phi k, I can write it like this. I can bring out my constants outside and calculate the inner product of each of those functions with phi k, each of those functions with phi k, first calculate the inner product, scale it by my coefficient and add it together. It's a direct consequence of linearity. From the definition of the inner product, it is obvious that this thing sigma Cj phi j minus f norm square, I can write it like that, right. It's just the inner product is just the norm square, right, sigma Cj phi j minus f, sigma Cj phi j minus f, right. Also, sigma Cj phi j, norm of sigma Cj phi j from j is equal to 0 to n minus 1. If this norm is equal to 0, this means that the square of the norm must also be equal to 0. If the square of the norm is equal to 0, then I can write the inner product is equal to 0, right. But we just saw that if the inner product is equal to 0, then the function itself must be equal to 0, right. So that means if the inner product is equal to 0, sigma Cj phi j equal to 0 to n minus 1 must be equal to 0, right. But since the phi j are linearly independent, this implies that all the Cj j equal to 0 through 1 through n minus 1 must be equal to 0, right. Then what does this mean? This means that if this is equal to 0, if norm of sigma j equal to 0 n minus 1 Cj phi j equal to 0, then all the Cj's must be equal to 0, right, and phi star f star is also going to be 0, right, because f star is constructed by this, right, sigma Cj phi j, right. So two functions are orthogonal if their inner product is 0. Thus a finite or infinite sequence of functions give rise to an orthogonal basis if phi I phi j is equal to 0 for all I not equal to j, and norm of phi I not equal to 0 for all I. We have something called the Pythagorean theorem. If the sequence is finite, the basis is for the basis is for a finite subspace of the infinite dimensional function space. So what I am trying to say is that if my function space is infinite dimensional, my function basis is going to be infinite dimensional. If my function space is, it's sort of trivial, but it's worth saying, right. So in case I have a finite dimensional function space, that is really a subspace of my infinite dimensional function space, and the basis of that finite dimensional function space are a subspace of the basis functions of my infinite dimensional function space. So if in addition to all these, so we talked about orthogonality, but in addition to these, if my norm of my functions is equal to 1, if the norm of my functions is equal to 1, then I have a orthonormal basis, right. I have an orthonormal basis. The orthonormal functions have, actually it's not really orthonormal, it's orthogonal, right. They have several desirable properties. For instance, they satisfy Pythagorean theorem. So what does it say? It says that if f and g are orthogonal, that is f comma g inner product of f and g are 0, right, and norm of f is not equal to 0 and norm of g is not equal to 0, then norm of f plus g square, I can write it in terms of an inner product f plus g, which I can write as f comma f, again using the linearity, right. I can write it as f comma f plus g comma f plus f comma g plus g comma g, and since they are orthogonal, f comma g and g comma f are going to be 0, and I am going to be left with norm of f square plus norm of g square, right. So if I have orthogonal functions, they satisfy this relationship. Norm of f plus g square is equal to norm of f square plus norm of g square. It is very similar to your trigonometry, right. So thus if phi 1, phi 2 through phi n are an orthogonal system, then norm of sigma j equal to 0 to n minus 1 Cj phi j square, I can always write like this in terms of an inner product, and if I perform this inner product, I am going to get sigma j equal to 0 to n minus 1 Cj square norm of phi j square. Why? Because if the inner product will involve, I again use the linearity, right, and the inner product will involve phi Cj Ck. Instead of writing it as j, maybe it would have been better if I wrote it as k, right. So Cj Ck phi j phi k, sum of those, and the terms where j is not equal to k, those inner products are going to vanish because of orthogonality, right. I will only be left with those inner products where the two functions are identical, right, and that is going to give me norm of phi j square. So, I am going to get something like this, right. Then if this thing is equal to 0, if the norm of sigma j equal to 0 to n minus 1 c j phi j square is equal to 0, with norm of phi j not equal to 0 for all j, then all the c j's must be equal to 0. You can see that, right. Why? Because I have these phi c1 square phi 1 square plus c2 square phi 2 square plus c3 square phi 3 square up to cn square phi n square. All the phi n squares I know are not 0, right, with norm of phi j not equal to 0. If norm of phi j is not equal to 0, norm of phi j square can't be 0. So, I have the sum of squares, right, sum of squares which are equal to 0. So, that means each of those terms have to be equal to 0, right. So, each cj c1 square phi 1 square must be equal to 0, c2 square phi 2 square must be equal to 0, and so on and so forth, right. And I know that phi 1 square, norm of phi 1 square is not 0. So, that means c1 square must be equal to 0, c1 square equal to 0 means c1 must be equal to 0. So, if this is satisfied along with this condition, then all the cj's must be equal to 0, right, that is one condition. But sigma cj square norm of phi j square equal to 0 implies, again I am writing this in terms of an inner product, sigma cj phi j sigma cj phi j equal to 0. So, inner product equal to 0, that means that this must be equal to 0, right. So, that means sigma j equal to 0 to n minus 1 cj phi j is equal to 0. Hence, what does it mean? That means this is equivalent to this, because this condition I got from this assumption, and this condition I also got from this assumption, right. So, hence 1 and 2 are equivalent. Thus, sigma j equal to 0 n minus 1 cj phi j equal to 0 implies that all the cj's must be equal to 0, which shows that an orthogonal system will always be linearly independent, right. An orthogonal system will always be linearly independent. Is the converse true? Well, certainly not, right. Every linearly independent system need not be orthogonal. There is nothing requiring that, but every orthogonal system has to be linearly independent, right. That should be sort of obvious, but this is a nice little proof. So, an important and very useful example of an orthogonal system is given by the sequence of functions cos jx, right, or for that matter sin jx is of your Fourier series, right. So, cos jx, you can know that all these cos x, cos 2x, cos 3x, they are all orthogonal to each other. Well, why is that? Well, the inner product of this system is given by, defined like this, f of x g of x integral between 0 to pi, right. That is, the weight function is equal to 1 and the inner product is over this interval, right. That the system is truly orthogonal can be easily proved. It is sort of trivial, but let's do it quickly. So, integral, so I am saying that each of these cos jx, cos kx, j not equal to k, if I integrate that, if I take the product integrated between 0 to pi, I am going to be at 0, right. So, integral 0 to pi cos jx cos kx, if I write it in terms of a sum of trigonometric functions, I can write it like that, right, half of this, and this is going to give me sin j plus k, this is going to give me sin j minus k. If I integrate sine between 0 to pi, I am going to get 0, right. So, they are indeed orthogonal, but if j is equal to k and both are not equal to 0, then cos jx cos kx is nothing but cos square jx, right. So, I can write as 1 plus cos 2 jx. This term is going to give me 0 on integration, because again it is going to give me a sine, but this term is going to give me a non-zero contribution, and that term is going to come out as pi by 2. So, again, so this is orthogonal, right. Any j not equal to any k not equal to j, I am going to get 0, any 2 and j, if I take the inner product of cos j with itself, then I am not going to get 0, right, I am going to get this. So, suppose I have a linear earlier on in this lecture, maybe in the first, maybe sometime in the first quarter we talked about Gram-Schmidt orthogonalization in the context of Gauss elimination, right. So, but particularly in the context of the QR method, right, we talked about Gram-Schmidt orthogonalization. But it actually the Gram-Schmidt orthogonalization, it is important for vectors, the same thing it is very important for functions also. Why? So, given a set of functions which I know are linearly independent, right, but not orthogonal, they are linearly independent but not orthogonal, I can always construct an orthogonal basis from those linearly independent functions using Gram-Schmidt orthogonalization, right, using exactly the way I constructed. Given n linearly independent vectors, I constructed a basis for the an orthogonal basis for the n dimensional vector space using Gram-Schmidt orthogonalization. I can do exactly the same thing for functions, right. The idea is exactly the same. So, given linearly independent functions, I can construct an orthogonal series of functions, right. When else do we get orthogonal functions? We looked at that earlier too, when we solved the eigenvalue problem, right. When we had a self-adjoint linear system, right, and we tried to solve the eigenvalue problem for that system, we found that the eigenfunctions were orthogonal, right. So, again the eigenfunctions arising from the eigenvalue problem of a self-adjoint linear system, right, self-adjoint system, they give me orthogonal functions, So, these are two ways we can generate orthogonal functions. So, for any sequence of orthogonal functions, or for that matter linearly independent functions, the problem of finding the best approximation to a function f in the interval a b, that is finding f star is equal to sigma j equal to 0 to n minus 1 c j phi j, such that norm of sigma j equal to 0 to n minus 1 c j phi j minus f square has a unique solution, right. So, this f star which gives me the best approximation, this f star is unique. So, given an orthogonal basis, right, given an orthogonal basis and given a certain function, right, the best approximation, the best guess that I can construct to f using those basis functions is unique. There is only one combination of coefficients, that is C0, C1, C2, C3 up to Cn, can only assume certain unique value which is going to give me the best approximation. There is no more than one. C0, C1, C2 have unique values, they cannot have more than one value, right, for that best approximation, right. To find the unique solution, we use the orthogonality property. What is the orthogonality? We just talked about that. That is f star minus f comma f star must be equal to 0, right. F star, why do I say that? Well, because f star minus f is my error, right. F star minus f is my error, and I know that f star minus f must be orthogonal to the basis spanned by the basis functions, right, by phi j. But f star is a linear combination of those phi j's, right. F star is a linear combination of those phi j's. Therefore, f star minus f, if I take the inner product with f star itself, that's got to be equal to 0, right, because I can write that f star as C1 phi 1 plus C2 phi 2 plus C3 phi 3 up to Cn phi n, right. Then I break it up. So, f star minus f comma C1 phi 1 plus f star minus f comma C2 phi 2 plus f star minus f comma Cn phi n. So, f star minus f comma C1 phi 1 has to be equal to 0, because f star minus f is orthogonal to the space spanned by all the phi's. So, it must be orthogonal to each phi as well, right. So, f star minus f comma C1 phi 1 is equal to 0, f star minus f comma C2 phi 2 is equal to 0, and so on and so forth. So, f star minus f comma f star has also got to be equal to 0, right. And then I have just written that, right. F star I have written as sigma j equal to 0 to n minus 1 Cj phi j minus f comma sigma j equal to 0 n minus 1 Cj phi j, that is equal to 0. And the fact that unique solutions exist can be proven in the following manner. Suppose the unique solution is given by this, right. Let us suppose that the unique solution is given by this Cj star comma phi j, and let us suppose C0, C1, Cn minus 1 be a sequence of coefficients such that at least one of those coefficients is not equal to the star values, right. So, suppose Ck is not equal to Ck star, right. Then sigma Cj phi j minus f, I can write it as sigma Cj minus Cj star phi j plus f star minus f, Cj phi j minus f, Cj phi j minus Cj star phi j. What is Cj star phi j? Cj star is my best approximation, so that is f star, right. So, I have minus f star plus f star, so that cancels out, and then I have minus f, right. So, I can write this as sigma Cj minus Cj star phi j plus f star minus f, since this is equal to f star, right. Recall, since sigma j equal to 0 to n minus 1 Cj star phi j satisfies the best approximation property, since it satisfies the best approximation property, f star minus f must also be orthogonal to the linear combination Cj minus Cj star phi j. I just talked about that, right. F star minus f must also be orthogonal to this, because this is after all a linear combination of the phi j's. So, if I take f star minus f and take the inner product with this thing Cj minus Cj star phi j, I am basically taking the inner product with each of the phi j's, right. So, what do we have? If we take norm of sigma Cj phi j minus f and square it, right, I can write it as sigma j equal to 1, j equal to 0 to n minus 1 Cj minus Cj star phi j square plus f star minus norm of f square. Why can I do that? Because these are orthogonal, right, because I just said that this must be orthogonal to that, right, and I express this as the sum of this and the sum of that, right, and each of this is orthogonal. Then I use my Pythagorean theorem and say that the norm of this must be equal to the norm of this square must be equal to the norm of this square plus the norm of that square, simply because these are orthogonal, right. So, what does that mean? So, this square plus that square, which must be greater than f star minus norm of f square, because what is this? This is norm of f star minus f square plus something, right. That something is either has got to be 0 or greater than 0, because it is a square, right. So, this thing has to be greater than f star minus f square. So, what does that mean? That means that this Cj phi j minus f, where remember these Cj are not all the optimal coefficients, right, they are not the best approximation coefficients. So, the difference of this from f in the Euclidean norm is greater than the difference of f star from f, which obviously means that f star is my best approximation, right. Thus, if f star minus f is orthogonal to phi j, which was the condition we started with, then f star is a unique solution to the best approximation problem, as any other linear combination of phi j's will give a larger approximation error, right. Any other linear combination is going to give me a larger approximation error. So, we have shown that a solution f star, if it exists, is going to be unique, right. The coefficients which define f star are unique, right. But can such a solution be truly found? That is, does it truly exist, right. So, we always concern ourselves with, in mathematics at least, they concern themselves with existence and uniqueness, right. Doesn't matter if something does not exist, I mean you can be proved to be unique, but just because it is unique does not mean that it does not exist, that it exists, right. So, you have to prove uniqueness as well as existence, right, but we are not, but we just do it very simply. So, for a solution to exist, the orthogonality condition must be solvable. So, there must be some Cj star phi j such that this condition is satisfied, right, such that Cj star phi j minus f, if I take the inner product with any of the phi k's, that has got to be equal to 0, right. So, this condition has to be satisfied. So, this gives rise to a linear system of equations. What is that linear system of equations? It is going to be something like this, just by expanding this out, right. Cj star phi j minus f comma phi k equal to 0, expanding that out, phi 0 comma phi 0 c 0 star, phi 1 comma phi 0 c 1 star equal to phi 0 comma f, right. I expand this out, I get a system of equations, and you can see this is a linear system of size n minus 1 times n minus 1, and this linear system is for the coefficient c 0 star, c 1 star through c n minus 1 star. And if I have an orthogonal basis, you will see that this linear this coefficient matrix. So, basically I want to find c 0 star, c 1 star, c n star minus n, right. So, these are my unknowns, right, and the coefficient matrix is phi 0 phi 0 term, each term in the coefficient matrix is phi 0 phi 0 phi 1 phi 0 and so on and so forth. Now, if I have an orthogonal basis, it is obvious that only the diagonal terms are going to be non-zero, each of the off diagonal terms is going to be 0, right. So, the becomes a diagonal system if the phi j are orthogonal when all the off diagonal terms vanish. Then the above system yields the solution Cj star is equal to phi j comma f divided by norm of phi j square, right, which has to exist. Why? Because this thing cannot be equal to 0, right, because we have assumed that phi j is not equal to 0, right. So, this thing has got to be different from 0, it has got to be positive actually, and if this thing is positive, then each of these Cj stars exist, right. I also wanted, so I proved the existence for when my basis functions are orthogonal. It can also be proved, it is slightly more involved, but it can also be proved that when my basis functions are not really orthogonal but are linearly independent, in that case also I can prove the existence of my solutions. So, I will start with that in the next lecture. Thank you.